Alrighty. Today we're going to be discussing how a 4 to 20 milliamp transmitter works. And, to get into it and lead into really what 4 to 20 milliamps is, and then kind of simple explanation of really what a transmitter is, a transmitter and sensor, and kind of how they work. Ultimately, what I'm going to be utilizing as my example is a pressure transmitter. And what a pressure transmitter is it has a sensor that detects the applied pressure and produces a small electrical signal. That signal is amplified and processed by the transmitter's electronics, which then converts into a standardized 4 to 20 milliamp output representing the measured pressure. Okay, and to simplify that a little bit further, you essentially have two parts to an instrument device. You have the transmitter and you have the sensor. And ultimately what's occurring is that you have a sensor membrane, which is measuring the mechanical physical property of a process, and in this instance, that is pressure. And based on that force that's being exerted on that sensor membrane, a very small electrical signal is being produced. The amplifier is amplifying it to make it more readily usable by the transmitter, and then that is sent out via a 4 to 20. So again, you want to look at all instrument devices in two parts. You have a sensor and you have a transmitter. Okay. Ultimately, how this integrates into our control system is based on a two-wire communication, that just being positive and negative, to the instrumentation device, and then back to the input card in, say, your DCS or PLC. What is a two-wire device? And what a two-wire device is, and what it means, is essentially the power and the signal are traveling on the same two wires, that simply being the positive and the negative. So who is supplying the power? The analog input card is usually supplying the power, and most of the time you will see 24 volts being supplied. Okay, and obviously you need power to power this, but you also need power for there to be a milliamp current. Okay, let's get into what a 4 to 20 milliamp is very objectively. And when I say that, I want people to understand what current actually is. And an example I could give you is, say we have a tank full of water, and the piping that is leaving it to, say, go to another tank or spin a paddle would probably be a better visual representation. But the piping leaving the tank are our wires. Okay, you could look at this input card as maybe the vessel, because this is where the voltage is coming from, and from this vessel we have piping leaving in the water. Inside that piping is the current, or electrons. And how we utilize electrons in our day-to-day life are in our light bulbs in our house, to just power things in general. Current is the stuff that is moving through our wires and performing work. So how we're utilizing the current in this instance is to basically send data. We are utilizing our instrument device to take a measurement and send this to our control system, our DCS or PLC. And based on this input, it will then make a decision. Okay? Depending on what type of control you are using, it will make a decision, or somebody will make a decision. Ultimately, we're taking a measurement and we're sending it somewhere. Okay? So one of the two main questions people may have about 4 to 20 is, what is it? Which it's simply just electrons. And how that works is that based on the physical measurement that's being taken, this transmitter is then manipulating the electrons within this current to coincide with the physical measurement that has been taken. So if we go to our table, we'll see that if we have ranged this transmitter, and when I say range, we have connected to this device with a communicator, say over HART. HART is a highway addressable remote transducer, which is a digital communication protocol that we can utilize to connect to this device and program it. And when I say program it, I'm talking about what we're telling it 0 psi represents, or what 25 psi represents, or what 50 psi will represent, 75, 100. And in this case, looking at our table, we're going to have it to where we have told this pressure transmitter that 0 psi is 4 milliamps, that 25 is 8, 50, 12, 75, 16, 100, 20. Okay. And why is this important? Well, because once we communicate to this device, we're going to need to configure our LRV and URV. And what those are our 4 to 20 milliamp values. Okay? So when this instrumentation device sees 0 psi, these wires will then have 4 milliamps on them. Okay? When it sees 100 psi, these communication wires will then see 20 milliamps on them. Okay? But you will need to physically go into this, connect to this device, go into this device and tell it that. Because it will know no difference. Okay? That being said, the input card, some integrator or programmer or controls engineer will need to go into this input card or the control system and designate what those milliamp values represent. What does 4 represent? What does 20 milliamps represent? And then it will display that accordingly. Okay. And that being said, that means that all this input card will ever see is milliamps. Okay. So if your scaling does not match, that creates a discrepancy. That creates a problem because this may be seeing 0 psi, but if you told this input card that, or control system, that 4 milliamps represents 10 psi, you're going to think there's 10 psi on your process. Okay? That's not good because now your information is not accurate and that could cause problems. So you need to make sure that what you have configured your 4 to 20 milliamp range to in this device, it is the same here. Okay? So another question is why 4 to 20 and not 0 to 20? Okay? If 0 psi is 4 milliamps, why isn't it just 0 milliamps? That would make things a lot easier, right? Well, not necessarily. What is the same as 0 milliamps? Well, you would have 0 milliamps if these wires weren't even connected. You would have 0 milliamps if nothing was connected. So, if you start off with a 0 baseline, you are now indistinguishable from having a circuit that is operating as expected versus it being in a failure state. That meaning a wire disconnected, this transmitter is no longer working, the wire has been cut. It's now indistinguishable. You have no idea in what state your circuit or loop is actually in. Okay, so we operate off a positive baseline of 4 milliamps. That meaning that when this is reading 0 psi, we still see current, which tells us that this is powered on, our wires are connected, our input card is good, and nothing has been cut or damaged. So it's what's expected. And then, say if a wire did get cut or this went bad and we see no current, well, you can have your integrator come into here and essentially say, hey, when you see anything less than 4 milliamps, go into alarm. And that'll cause the display on, say, the board to go start flashing red, and this will bring your attention like, hey, your measurement device is no longer operating as it should be, or there's a problem with the wires. And then you as a technician will go out there and troubleshoot it as needed. Okay? Because, again, all this will ever see when utilizing a 4 to 20 milliamp output is milliamps. All it knows is what you tell it that those milliamp values represent. Okay? And to get into more functional explanations, milliamps are measured in series. Okay? Voltage is measured in parallel, milliamps in series. So this DCS/PLC analog input card must be in series with the communication wires of this instrumentation device. And what that means is positive to positive, negative to negative. Okay? That is series. Okay? If I wanted to take my multimeter and see what the milliamp output is from this device, I would disconnect one of my wires from either my negative or my positive side, one of them, put one of my leads on the negative terminal and one of my leads in my other lead on the wire that was disconnected. And that will put you in series with this transmitter. And the DCS is going to be representing it as a pressure because a programmer went in there and said, hey, this milliamp value represents this pressure. But my multimeter is going to be reading a milliamp value. So in this instance, if we were reading 12 milliamps, that would mean we should have 50 PSI, okay? So if we got in series, and this is reading 12 milliamps, and then in our control system, we would then see 50 PSI if we're ranged 0 to 100 PSI. Because we have went in here and said, hey, our 4 to 20 milliamp range is 0 to 100 PSI, and we have said the same thing here. And you can confirm this by looking at the pressure on the display, because this is not communicated data from something else. This is a first-person representation from the transmitter, and it would say 50 psi. So this says 50 psi, this would say 50 psi, and this would say 12 milliamps, which is 50%. 50% of 100 is 50 psi. So that's kind of how it works. And then this line designates the separation, and what connects it is the two-wire communication, okay? So fairly simple. This is taking a measurement. This is sending it via milliamps. It's only current. So that being the case, this only being current, you have to go in there and tell it what the current represents. That's really important. Then you have a concept of sourcing and syncing, which essentially, or active and passive, and this is a passive device. That means that it needs to be powered. It is receiving power from the source. This is sourcing. Okay, this is syncing essentially, or this is active and this is passive. Okay, and what that means is, right, pushing power, receiving power, but it's manipulating the current within this loop to coincide with what the sensor is measuring. Okay, so it's fairly simple, not too crazy or complicated. Again, you would need to configure your URV and LRV, and that's how this will then function. And you can confirm this, by screwing in, say, a crystal or like a flue can pump with a process calibrator and pump it up and, pump it up to 50 psi, make sure you're getting the right milliamps, and then make sure you're seeing the correct thing on your HMI or control system. Okay. Just quickly, there are other ways to communicate data via digital communication protocols. You have analog communication, that being like, say, voltage and current. Current is more widely used than voltage, just because of like what I said at the beginning. You don't pick up as much noise and you don't experience voltage drops, which will diminish your signal over great distances. But you have different types of digital communication protocols. You have Profibus, Modbus, Foundation Field Bus. You have HART, which again is what you're going to utilize a lot of the times, because a lot of these transmitters, if they're 4 to 20, then a lot of them are HART, which means you can get in series or in parallel with this device and pick up on the HART communication signal and talk to this device and look at diagnostic codes, look at settings, see if there's anything wrong with it, just make sure that this is set up correctly and troubleshoot as needed. And again, if I haven't already mentioned this, I may have already, but this can also interpret HART data, right, up to 4 dynamic variables, but you need a 250 ohm resistor in the system, as well as this needs to be a HART capable card. So not only can this utilize and see HART data, but you can utilize the HART protocol to connect and communicate with this device and set it up. Very important, very useful, and super simple once you get the hang of it. I think that's it for today's discussion and video. So if there's any questions that you have, feel free to comment and I will answer them as soon as I can. And thank you for watching. I appreciate it. Bye-bye.